Gas pressure is caused by collisions of gas molecules with a surface. And we could say such as the inner or outer walls of a container. And that's exactly what happens here. And let's explain these. So I think we did this one first. Okay, now the first one we did, if we go through the procedure of what we did, remember we put in a small amount of water. And we heated the water up until it turned into a gas. Now once it turned into a gas, the key to this one working is that you have to heat it up long enough so you displace all of the air in there. And the only thing that should have been in this can at that point, if I did that long enough, would have been
H2O.
H2O in the gaseous phase. So again, if I heated this up long enough with the water in it, we should have removed all of the air and it should have been replaced with gaseous water. So now, if we were to talk about gas as a liquid versus gas as a, not gas as a liquid, water as a liquid versus water as a gas. If this is water as a liquid, water as a gas would look like what? They would be out here. They would be further apart. So in liquid water, the molecules are pretty much into contact with each other. In gaseous water, those molecules are much further apart from each other. In fact, what you can do, the ratio is about 1700 to 1. 1 milliliter of water in the liquid phase will turn into about 1700 milliliters of water in the gaseous phase. So it's a ratio of about 1700 to 1 in terms of the difference in volume. So now that I have the gaseous water in the can, I invert it over to this bucket of water, and this is just ordinary water we got out of the faucet over here. All of a sudden that gaseous water in here will turn from a gas back into a liquid. When it turns from a gas back into liquid, that creates a vacuum on the inside. Anybody know what a vacuum is?
A vacuum is an absence of any type of phase matter.
Absence of matter is what it boils down to, exactly. And it's not going to be a complete absence, but we basically removed pretty much all of the gas molecules we could. And if we converted that gas back into liquid, there's nothing then. Remember, if we talk about gas pressure, there's no longer any collisions that are on the outside walls or on the inside walls. The only place that the collisions are occurring are on the outside. And since the only place they're occurring on the outside, basically that pressure winds up collapsing the can. So the pressure on the outside of the can is greater than on the inside of the can. Well, let's talk about the other one next. The next one we went to, this one here, we started with air. We heated that air up. We inverted it into the bucket of cold water, and what happened? Nothing really, other than, remember when I turned it right side up, we heard a little bit of water had gone back into the can. And it's simply due to the fact that if we started with air, air is already in which phase? Gaseous phase. When we heated it up, what do you think happens to the spacing between those molecules?
Stays the same.
About the same. They actually do wind up becoming a little further apart, but not a whole lot of difference there. So it was a gas to begin with. It's still a gas, and if I cool that gas back down, well, it was enough to draw water up into the inside of it, but it was not enough to cause the can to wind up collapsing. So then I put the water back into here. We heated it up, turned that liquid water into a gas. And once we turned it into a gas, of course the key there is to displace all of the air. And so the only thing that's inside of here would have been gaseous water. We invert it into here again. That causes that gaseous water to convert back into a liquid. When it does so, there's no collisions on the inside. The only collisions occurring are on the outside, and it collapses. Now, I don't know if you've ever been to the State Fair before, but the University of Minnesota Physics Club does this very same demo, except they don't use a pop can. You know what they use?
Like a boil drum?
Yes, they use like a 55-gallon drum, big steel drum, and they heat up the water. And if you want to see something really amazing, watch a 55. Have you seen that one?
I just kind of my logic, just kind of like that.
Yeah, yeah. So they take a big 55-gallon drum, which, I mean, we're talking, that's like trash can size, and they collapse down, and you get thick walls, and I mean, it's quite a bang when that thing winds up collapsing. But I don't have a steel drum here to show you. If I did, you know, maybe we do that sometime if we have it. But no, part of the reason why it's so dramatic has to do with gas pressure. We really don't realize what the gas pressure is. This is a metal bar that my late uncle made for me. He dealt with scrap metal, and I asked him to make it to some exact specifications. This weighs 14.7 pounds, and if we measured its cross section here, it's 1 inch by 1 inch, which means that this area is
1 inch cubed.
1 square inch, exactly. So if it's 1 square inch and this weighs 14.7 pounds, that means when it sits on this floor, it's exerting a pressure of
14.7 pounds per square inch.
exactly 14.7 pounds per square inch, and that's what the atmosphere is exerting on us all of the time. In fact, Dave, if you were to set your hand up, put your hand on here, try to set this on there. Does it feel heavy?
It's pretty heavy.
And I could put this all over on you right here. And as I do that, it turns out that that pressure, at 14.7 pounds per square inch, is something that's acting on all of us in here, on every square inch of our body, all the time. And so we just saw the amazing effect of what that is. So if that pressure is so large, then the next question is, why don't we feel it? Why don't we feel that pressure? Anybody know?
Pretty even. Gravity.
Not gravity.
Well, I was just thinking, like, if we didn't have that pressure on the outside of our body, all of our atoms would burst apart and we would spontaneously combust.
Exactly. If you go out into space, boom, we're just going to vaporize.
So the only thing keeping us as one specific, like, say, one human, is the fact that there's enough pressure on the outside of our bodies to actually keep everything on the inside, rather than everything all over the place.
True. But we still don't feel it though.
Yeah.
And part of it's because the pressure is something that acts in all directions. Okay, if I hold my hand out here, not only is that pressure pushing down on my hand, but it's being pushed up on with an equal amount. It's pushing this way, this way. The only thing that's moving my hand is gravity and then whatever I'm doing with my muscles, but it's something that acts in all directions. And so like when you breathe, what you're doing is you're changing the size of your rib cage. If you expand the size of your rib cage, what happens to the air?
There's more air that fills up the
It's
inside.
sucked in.
The air rushes in. Okay, and that's because as you expand the rib cage, the pressure on the inside of your lungs is less than outside of the room, and so the air then rushes in. When you decrease the size of your rib cage, then what happens? Air rushes out because the pressure on the inside of your lungs exceeds that of the atmospheric pressure, and the air winds up rushing back out. And so we are dealing with air pressure all the time through breathing, simply by changing the size of our rib cage, which is what causes the air to move in and air to move back out all the time. Now, as far as some of the units that we work with here, some of the units that we work with when it comes to pressure is the units of atmosphere. And now you don't need to write all of these down. You're going to find these on your conversion sheet. Right here, if you pull out your conversion sheet, you're going to see a number of pressure conversions here. And so the unit of the atmosphere we abbreviate as 1 ATM. And this has a value of 14.7 pounds per square inch, which we also write as 14.7 psi. This is also equal to 29.92 inches of mercury, which is the same as 760 millimeters of mercury. Now, as far as where these things come from, and there's a reason actually why we use mercury. It's because mercury is the most dense liquid that there is. And so this here is a mercury barometer. And in a mercury barometer, what we do is this. First of all, this upper portion is a vacuum. Basically, we take a tube, and we create a vacuum in it, and we place it into a pool of mercury. Once we place it into a pool of mercury, if there's a vacuum up there, what happens to the mercury then in that tube? Yeah, it goes up. And actually, when we talk about gases, we should never talk about them sucking. We should say that the reason why the mercury winds up going up inside of this tube is because what happens? The atmospheric pressure is pressure. It's causing pressure here on the surface of this pool of liquid. And in this vacuum, there's nothing acting on the surface, so what happens then is that the liquid in that column will rise. And the height of that liquid in that column will change depending upon the atmospheric conditions. If you are reading your news online or the weather online or you watch it on TV, you'll hear about the conditions of the atmospheric pressure. And they'll say, well, the barometric pressure is 29.92 inches. And what they're talking about then is this height of the mercury in the column. It is the height from the surface of the mercury up to this height right here. And if we're under conditions of high pressure, what does that do to the strength of the number of collisions that are occurring here with the surface? More collisions or harder collisions or lesser collisions with less force? What do you think it would be? Right, high pressure is going to create more collisions with that surface. And if we have more collisions with the surface, what's going to happen to the height of mercury in this column?
It's going to go up.
It's going to go up, exactly. And so then we could have something like, it's fair outside today, right? Sunny out? No, not sunny? No, I thought it was. See, I even have an office with a window and I don't remember. But if it's a really sunny day, usually we're under conditions of high pressure and that column would be taller. And if it's a really crappy day outside, then we are under conditions of low pressure. And the primary reason why we're under conditions of low pressure is because when the weather's crappy, what else is going on outside? You've got rain or snow or fog or something like that. And what is rain, snow, fog made out of?
Precipitation.
Yeah, which substance? Water. Right, water in the gaseous phase. And it turns out that water molecules are lighter molecules. They are 18 grams per mole versus the normal molecules in the air, which is N2, which is 28 grams per mole, and oxygen, which is 32 grams per mole. So when you have a lot of water in the air, then those molecules are lighter, and as a result then those lighter molecules, just like if you took the lightest person in here, ran into me, you're probably not going to move me a whole lot. You take the bigger person, run into me, you're probably going to move me. So it's the same thing. When we talk about molecules, those lighter molecules are going to cause that column to not rise up as far, and we have conditions of low pressure. So this value here, though, that we're talking about, this 1 atmosphere, this here is called the average atmospheric pressure at sea level. This is the average atmospheric pressure at sea level. Now, as far as how we calculate pressure, pressure is calculated, or not calculated, but we define it here first. We define pressure as being the force exerted. It's the force exerted per unit of area. Force exerted per unit of area. So now, in mathematics, if we looked at the word per, what does the word per mean to do in math? It means to divide. So we want a formula here. We would say that pressure is equal to, what's going to go on top?
Force over area.
Force over area, exactly. Force divided by area. So this takes us to 3 questions I think we have left on the Socrative app here today. And I have a wood block over here, and I'm going to show you 3 orientations of this wood block. And we'd like to know which orientation, given this formula, would exert the greatest pressure on the surface of the bench. And you can talk with your neighbors here if you need to. Here's A, here's B, here's C. So again, here's A, here's B, here's C. Which one is exerting the greatest pressure on the surface of the bench? Here's A. Here's B. Here's C. Talk with the neighbor if you need to. We'll give you about 30 seconds. Talk with the neighbor. Here's A. Here's B. Here's C. A, B, C. 10 seconds. Here's A. Here's B. Here's C. Lock in your answers. We'll go 5, 4, 3, 2, 1. It is A. And it is A because less area, that's right. So, if you look at this equation, area sits down here, pressure sits here. If we have a smaller area, that makes the pressure bigger. If we have a smaller denominator, that makes this pressure, this value, larger. How about if we had put more force on this? What does that do to the pressure?
Also increases it.
That will also increase it as well. Exactly. Which then brings us to some terms. According to this equation, pressure and area are, talk to the neighbor if you need to, are they inversely proportional, directly proportional, or hardly proportional? Do you get your answers locked in? We'll count down. 5, 4, 3, 2, 1. They are inversely proportional. And if they're inversely proportional, what that means is one goes up, the other will go down. There's actually more to it. When we use the word proportional with it, when we say when one goes up, the other goes down, that's just simply an inverse relationship. But if we say that it's an inverse proportion, it has a further implication. That means that if we double one variable, the other one will be half. And if we cut one by a factor of 10, that means the other one will be multiplied by 10. Right. That's what an inverse proportion means. So pressure and area, we say, are inversely proportional to each other. Then keep looking at the equation. According to this equation, pressure and force are, get your answers locked in. 5, 4, 3, 2, 1. All right. Isn't that a great way to end the class? These here are directly proportional. That means if you double one, the other one will double. If you cut one by a factor of 10, the other one will be cut by a factor of 10 as well. So great job. That's it here for today. We ended the class on Thursday talking about these conversions. When I looked at it, it looks like I forgot to write this last line of conversions on, but we don't need to write these down because where can we find these?
In the back of our periodic table.
Back of your periodic table, exactly. So if you pull out your conversion sheet, anybody need a new conversion sheet? You're going to find these down here for pressure. New conversion sheet, anyone? Anyone? Anybody else? All right. So now, if we look at these conversions, what we'll see is that 1 atmosphere is equal to a whole bunch of different things. And consequently, we can use that relationship to do a number of different conversions. And so what we're going to do here is we're going to take a pressure of 11.7 psi, which again stands for pounds per square inch. And we want to express this in units of millimeters of mercury and units of pascals. So we're going to start with the first one here. We'll start with what we're given. And what are we given?
PSI.
How many PSI?
11.7.
All right, so remember with dimensional analysis, we always start off with what we're given. And for the first answer, what are we looking for? Well, we're looking for two different things. So what's the first one we should do? Do we know any of the two things we're looking for?
Millimeters of mercury.
And pascals. PA stands for pascals. So for millimeters of mercury, let's set this one up. We're going to look for millimeters of mercury. Now, in order to convert from PSI, pounds per square inch, to millimeters of mercury, we need a conversion factor. Now up here, all of these conversions are equal to each other. Notice their equal sign. And in those, we see the 14.7 psi is equal to 760 millimeters mercury. So we can then, if they're equal to each other, we can use them as a conversion. On the bottom, we put in
14.7 psi.
14.7 psi, and on the top, $760 millimeters of mercury. Once we do that, what happens to units?
Cancel.
Which ones cancel?
PSI.
PSI cancels. Once they cancel, this is set up then to solve for millimeters of mercury. We take 760 times 11.7. We divide it by 14.7. And we're left with an answer of, and how many sig figs should be in the answer?
3.
So off the 3 significant figures, this would be 605 millimeters of mercury. Now, once we get this answer, we should ask ourselves if it makes sense. Well, 11.7 psi is a little bit less than 1 atmosphere, and looks like 605 is also a little bit less than 1 atmosphere as well, so this would be an answer that makes sense. Any questions? All right, you do the next one, and you'll see that your choices there on the Socrative app. I'm going to take 11.7 pounds per square inch, convert it to units of pascals. Now help each other out if you need to. 5, 4, 3, 2, 1. Correct answer is choice B, 8.06 times 10 to the 4th pascals. If you want to set this one up, this is how this one looks when it's set up. We are trying to convert from PSI over to units of pascals. We need to have two quantities that are equal to each other here, so they can be used as a conversion factor. We see that the pascals right here, there's 101,325 pascals. for every 14.7 psi. We can then use it as a conversion. Psi cancels out. And by the way, why do we express this in scientific notation? Yes?
Because you only want it out to three significant figures.
Right, we want to show this one out to 3 significant figures because we're given the 3 significant figures here on this one. So any questions on this problem?